Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we have discussed about engineering tribology subject in previous sessions. We have learned friction and wear and lubrication and corrosion and engineering materials topics. And also we have discussed about various questions related to these topics. Now in this session, I want to revision of numerical problems. Already some numerical problems we did in the previous sessions. So again, we will solve some problems related to this friction, wear, and lubrication. So engineering tribology involves these three fact parameters: friction, wear, and lubrication. Clear? So the engineering tribology nothing but is a study of friction and wear and lubrication, and additionally corrosion material and selection, the corrosion and the selection of materials. These topics are very important. Now in this session we will see the numerical problems related to these topics. Clear? The problem 1. Suppose friction force calculation. How to calculate the frictional force? So you know the friction is nothing but a resistance force oppose the applied force. So whenever you are applying force on a object, it tends to move, but some force opposes this movement. So thus force is called as frictional force. So how do you calculate this frictional force? How much frictional force acting? So a block of mass m 5 kg is placed on a horizontal surface. So block is placed on a horizontal surface like this. This mass is 5 kg. The coefficient of static friction between the block and the surface is 0.3. So in between these surface and block, the mu is coefficient of friction is 0.3. The coefficient of kinetic friction, that is mu k, between the block and the surface is 0.25. One is the block and the surface, and the kinetic friction, this is static friction, under it is in a stationary place, stationary motion. So that is nothing but static friction. So just placed this block on the surface, there is no force and there is no movement. Then the friction is 0.3. So whenever we applied force, that is kinetic friction. So the coefficient of friction between the block and surface is 0.25. So here he has asked the maximum static frictional force. First to calculate static frictional force, and second one is the frictional force when the block is in motion. So frictional force when the block is in motion need to calculate, and static frictional force. How do you calculate? The maximum static friction force, that is given by equation mu mg. So actually the frictional force is equal to mu multiplied with Rn. So there mu is static coefficient of friction, and Rn is normal reaction force. But here the normal reaction force in terms of mg. So where g is equal to 9.81 meters per second square. that is acceleration due to gravity. So the kinetic frictional force, that is representation is Fk, is given by mu k mg. So here the mu is static coefficient of friction. Coefficient of friction when it is in stationary, that is a static condition. Static. So another one is mu k, kinetic. So mu k mg. So now substitute these values, given values in this equation, you will get a frictional force. So what is the first one? Mu is static condition 0.3, 0.3 multiply with mass is 5 kg multiply with g 9.81. So here you calculate, you will get nearly 50 frictional force, you will get newtons. Similarly, in this equation substitute the mu k value 0.25 multiply with 5 multiply with 9.81. This one also you will get a value. So approximately you take 25 by 100 into 5 into 9.81. 12.5 something. Clear? So the frictional force is reduced when compared to the static frictional force. Clear? The maximum static frictional force, however, and the frictional force when the block is in motion, second one also we have calculated. So like this you need to calculate. Next, problem number 2, wear volume calculation. A steel pin slides against a steel plate with a load of 100 newtons and the sliding distance is 500 meter. The wear coefficient is 1 into 10 to the power minus 8 mm cube per Newton meter. 10 to the power minus 8 mm cube per Newton meter. So here what he has asked, find the wear volume. How do we calculate the volume? The wear volume is given by V is equal to K into L into T. So here actually practically we will calculate this wear and reflection by using pin on disc. A pin slides on a disc. So whenever this pin slides against a steel plate, that is steel disc, that is in rotary motion, supply load and sliding distance, you can change the sliding distance, that is 500 meter. The wear coefficient is given. So now calculate the wear volume. So the V is equal to K. So 10 to the power minus 8 multiply with the L load 100 newtons multiply with the diameter. So need to only simply substitute the values in wear volume formula. But you should know this formula. If you don't know this formula, you can't calculate. So now calculate this one. 10 to the power minus 8 into 10 square. So 10 to the power minus 6 into 500 mm meter. So the 5 into m square again, 10 minus 4. So this is wear volume in mm cube per Newton meter. Next, problem 3, lubrication film thickness. In a lubrication part, there are two types. One is hydrodynamic lubrication and then body lubrication. So for hydrodynamic lubrication, example is journal bearing. It has a shaft that is the diameter given 50 mm and a length is 100 mm. The shaft rotates at a speed 1500 rpm. The shaft rotates inside the bearing. The lubricant viscosity is 0.1 Pascal. So the radial clearance, it is C, between the shaft and the bearing is 0.1 mm. So we have seen in the theory part. So this is journal and bearing. So the bearing center and the journal center, there is eccentricity, the distance between these two centers. So here the lubricant will present. So this is called as journal and then bearing lining. So this lubricant present inside, that viscosity 0.1 Pascal. Speed also given. The radial clearance between the shaft and the bearing also given, the radial clearance, that is 0.1. So he is asked find the minimum lubrication film thickness. So what is the film thickness here? The lubrication film thickness. It is minimum film thickness. The solution is the minimum film thickness in aerodynamic lubrication can be estimated using the following formula. C into 1 by 1 plus 2 pi n d efficiency, that is so lubricant viscosity by LP. Here P is the bearing pressure, and for this problem assume uniform pressure distribution. So like this, you need to calculate here, substitute all values. So you know N and D viscosity and bearing pressure need to assume, and P, the bearing pressure given, and P bearing pressure need to assume here length, the length of the bearing also given. So no problem. Clear? So substitute all these values in this formula, you will get the minimum film aerodynamic lubrication film thickness you will get. So problem number 4 is related to surface roughness measurement. So the surface roughness profile is measured and the arithmetic mean roughness is found to be 2 micrometer. So the total evaluated length is 10 mm. So the average roughness height over the total evaluated length. So what is asked? So the find the average roughness height over the total evaluated length. The surface roughness is a very important parameter in tripology. If not having a smooth finish, the surfaces, which surfaces are in relative motion, there is a friction. That is depends upon this roughness. So need to measure this roughness profile. The arithmetic mean roughness means summation of all values and then find the mean. You will given here 2 micrometer and length also given. So find the average roughness height over the total evaluated length. So that by using this equation, the arithmetic mean roughness is given by RA is equal to 1 by L integral 0 to L. So minimum limit is 0 and the maximum limit is L into y of x dx, where the y of x is the roughness profile and L is the evaluated length. For a simplified calculation, if the roughness profile can be approximated by discrete measurements, it can be found by averaging the absolute values of the deviations from the mean lines. So the equation is RA is equal to 1 by L integral 0 to L, so mod of x ds. You will get roughness value. So in previous problem, the arithmetic mean roughness RA is given and evaluated length also given 10, but he has asked the average roughness height. The roughness height over the total evaluated height. Okay, the y-axis is the roughness profile. The L is the evaluated length. The problem number 5, bearing load capacity. How do you calculate this bearing load? We have discussed about the aerodynamic bearing. So in this, the journal rotates inside the bearing. Whenever the lubricant is present, there is chances of metal to metal contact. There is a minimization of metal to metal contact. If not present lubricant, there is a chance. So based on this, he has given here problem that aerodynamic bearing supports a radial load, that is W up to 1000 Newton. The journal diameter, that is D, is 75 mm and the length is 100 mm. So the lubricant viscosity is given 0.05 Pascal second. The journal rotates at a speed of 1000 rpm. So the radial clearance is 0.15 mm. So here the given data is a radial load, one is 2000 newtons and journal diameter 75 mm. The length is 100 mm. Lubricant viscosity is 0.05 Pascal second. The journal rotates at a speed 1000 rpm. The radial clearance is 0.15 mm. So the total load, the load capacity of the bearing, the load capacity of a aerodynamic bearing can be found using the Sommerfeld number. So number you can write like this, where P is the bearing pressure. The load capacity can then be estimated based on the bearing design charts or empirical formulas that relate the Sommerfeld number to the load capacity. Next problem, next problem related to this bearing. Film thickness in a journal bearing. The specifications are given journal diameter 100 mm, the bearing length 150 mm, and radial clearance 0.1 mm C, and journal speed N 1500 rpm, and lubricant viscosity 0.02 pascals. The journal diameter given D, and the length and the clearance C and N, and viscosity. So calculate the minimum film thickness and maximum film thickness. H minimum how much and X maximum. So solution, see here minimum film thickness, how do you calculate? Given formula where C is the radial clearance and epsilon is the eccentricity ratio. So H minimum is equal to 1 minus eccentricity, and H minimum is equal to C into C multiplied with 1 minus epsilon. Where C is the radial clearance, epsilon is the eccentricity ratio. Assuming full hydrodynamic lubrication, epsilon can be estimated using the Sommerfeld number, which is a more advanced concept. However, in many cases, the minimum oil film thickness can be estimated as approximately the radial clearance itself, a rough approximation. That is, H minimum is equal to 0.1 mm. H minimum is equal to 0.1 mm. That is C. So the maximum film thickness H max is equal to C into 1 plus epsilon. Assuming epsilon is 0.8, typical value for hydrodynamic lubrication, H max is equal to, now substitute the given value C 0.1 mm and then epsilon 0.8. The epsilon can be estimated using the Sommerfeld number. Clear? So assuming here number epsilon 0.8. Now you will calculate, you can calculate X maximum film thickness. So you will get 0.18 mm. Next, problem number 2 related to this pressure distribution inside a slider bearing. Pressure distribution in a slider bearing A, slider bearing with the following specifications. The bearing length 300 mm given. Let take L. Bearing width B 200 mm. Sliding speed velocity 5 meters per second. Lubricant viscosity, that is 0.015 pascal second, and film thickness H naught 0.02 mm. So now calculate the maximum pressure developed in the lubrication film. So how much pressure developed inside the lubrication film need to calculate for the given specifications. The solution is the maximum pressure inside a sliding can be found using the Reynolds equation for aerodynamic lubrication, but a simplified form for a flat slider bearing under steady conditions. So that is P max is equal to 6 epsilon mu L by H square. So here zeta is the dynamic viscosity given in the problem. U is the sliding speed 5 meters per second given in a problem. And then L is the length of the bearing in mm, convert into meter. And H is the film thickness, that is 0.02 mm, convert into meter. So 0.0002 meter. Now substitute in the P maximum. P maximum 6 multiply with 0.015 and 5 multiply with 0.3 divided by H square, the film thickness square. So we will get value like this. Then convert into megapascal. So 1 megapascal is 10 to the power of 6 Pascal. Okay, like this, how to solve this problem? It's related to the bearing pressure distribution. So by using this formula. Next topic is numerical problems related to surface roughness. Up to now we have seen wear and friction. So the surface roughness is a crucial parameter in manufacturing and engineering. Influence the performance, appearance, and durability of mechanical components. So in manufacturing engineering, it is very important parameter. It influences the performance. If the surface roughness is good, the product will perform with high efficiency. Why? Because less wear and less friction will be developed. And if surface roughness is good, the product appearance also will be good. And durability also will be increased. So that's why in mechanical engineering, mechanical components, all mechanical components require this surface roughness. So the calculating average roughness values. In previous topic in problem solving, have seen average roughness directly he has given formula, but in this need to calculate average roughness. In the previous problem he has given a machine surface has the following profile heights in micrometers. So measured at regular intervals 2 and so the measured the profile heights 2. First one is 2. Profile height 2 and 4 and 6 and 3 and 5 in micrometers. So in this, what he has asked to calculate the average roughness of the surface. First you take sum of the heights. Total sum of the heights you calculate. So that is 2 plus 4 plus 6 plus 3 plus 5. 2 plus 4 plus 6 plus 3 plus 5. So you will get 20 micrometers. So number of measurements, n is equal to 5 newtons. So the number of measurements 3, 4, 5, total 5. So average roughness is sum of the heights upon number of intervals. So total sum is 20 by 5. So 5 micrometer. Obtained this value. For this type of problems, first need to take average values, the sum of profile heights, and then calculate the average roughness by using sum of these intervals, sum of profile heights upon total number of intervals. So next problem number 2. So calculate root mean square roughness. The previous one average roughness. Now this one is root mean square. Consider the same set of measurements 2, 4, 6, 3, 5 micrometers. So calculate the root mean square roughness. First square the heights. Same as previous problem. But here considering square. But in the previous problem there is no square. Only sum of heights we have taken. For this 2 square plus 4 square plus 6 square plus 3 square plus 5 square. So much here. Calculate 4, 16, 36, 9 and 25. So we will get some 20, 56, 56 plus 9, 65, 65 plus 25, 90. Sum of squared heights. First square the heights and then sum of squared heights. The total squared heights is 90. Now calculate the root mean square roughness value. So average of squared heights and root mean square. So average of squared heights. In previous case, what you have done here, the sum of heights, number of measurements taken, the average roughness. Total sum by total 90. Here, the average of squared heights. So 90 1, total how many intervals? 3, 4, 5. 5. So 5, 18. The root mean square value is 18. The average of squared heights gives 18 micrometer. Micrometers. Next problem. So in this previous problem, calculating average roughness we have learned, and root mean square roughness value also we have studied. Next in this problem, determining the surface roughness from a profilometer reading. So how to calculate the surface roughness value from a profilometer. So given here profilometer measures the surface roughness of a sample and provides the following values for the peak to valley height PV and the average roughness value. So the profilometer measures the surface roughness of a sample and provides the following values for the peak to valley height. If the peak to valley height is 20 micrometers and the average roughness is 4 micrometers. So calculate the peak to valley height as a multiple of the average roughness. So given the height 20, average roughness also given. Only he has asked peak to valley height. So the given peak to valley height PV is 20 micrometer. The average roughness value is 4 micrometer. Multiple of average roughness 20 peak to valley height upon average roughness is equal to 20 upon the average roughness. We will get the multiple average roughness. So the peak to valley height is 5 times the average roughness. So the average roughness value is 4. So the multiple is here 5. So that is the PV is 5 times the average roughness value, that is RN, 5 RN. Clear? So like this need to calculate. Next problem number 4. Estimating surface roughness from cut depth. How do you calculate the surface roughness from cut depth? Now we are learning. So how to calculate the surface roughness? See the first problem. If you observe here, so that is bearing. The surface roughness, calculating surface roughness whenever the given profile heights and intervals, then you can calculate the average roughness. And second one is calculate root mean square. So whenever given the set of measurements, root mean squares you can calculate. So average of squared heights and root mean square. Now next surface roughness value can calculate from a profilometer reading. How to calculate? Determining the surface roughness from a profilometer reading you have seen. Now in this, estimating the surface roughness from a cut depth. So whenever you are doing the machining, there occurred this cut depth. A turning operation is performed with a cutting depth of 0.2 mm. If the cutting tool creates a roughness of 2 micrometers for 0.1 mm of cutting depth, estimate the surface roughness for the given cut depth. The turning operation is performed with a cutting depth of 0.2 and the roughness is 2 micrometers per 0.1 mm. So how do you calculate this one? Let's see the roughness for unit cutting depth. The roughness for 0.1 mm is equal to 2 micrometers. The cutting depth is equal to 0.2 mm. The scaling roughness, the cutting depth given 0.2 mm and scaling roughness is 2 micrometers multiplied with cutting depth upon this roughness for 0.10 mm. So we will get 4 micrometers. Thus the estimated surface roughness is 4 micrometers. So roughness for 0.2 micrometers, take this 2 micrometer and cutting the micrometer roughness for 0.10 mm value, and here cutting depth upon roughness for 0.1 mm. So roughness value, the roughness of 2 micrometers for 0.10 mm of cutting depth. So they were given 0.10 mm. So 0.2 by 0.1 into 0.5 micrometers we will get. Next, converting surface roughness units. How to convert the surface roughness units? So convert the surface roughness value of 6 micrometer roughness value, average roughness value to micro mu in micro inch roughness values. The conversion factor is 1 micrometer is equal to 39.37 micro inch. So conversion, surface roughness inch is equal to 6 micrometer. So the surface roughness value given 6 micrometer. Multiply with 1 micrometer, that is 39.3 inch per micrometer. So you will get approximately 236.22. Therefore, a surface roughness of 6 micrometer roughness average value is approximately 236.22 micro inch roughness average value. So how do we convert this one? Here micro inch surface roughness is equal to 6 micrometer given 6 multiply with so 1 micrometer. Clear? So this is, you will get 236.22. So this is the surface roughness value. Like this, need to convert the surface roughness units into micro inch. So these are the references I have taken for this PPT. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.